Okay, well, welcome to the next session of our workshop. I am Dave Peralt. I'm a faculty member in electrical engineering and computer science at MIT, and my own personal work is on power electronics, energy conversion, and their application to advance all kinds of systems, and especially improving the energy efficiency of systems. So today's workshop is of great interest to me. And so I'm very happy to be here and to see all of the interesting work we're seeing today. Next slide, please. So just to show you where we are in the workshop, in the Climate Impacts of Computing and Communications workshop, this session is session 5, and it's really focusing on energy efficient systems. Next slide, please. So if we think about things at a systems level, we saw earlier today, and I think our earlier host Muriel Medard mentioned the magic of commuting and communications, and really technology has advanced to the point where computing systems and communication systems and what we do with them are almost indistinguishable from magic. And how have we gotten here? In part, we've done that by taking really tremendously challenging problems and breaking them down into smaller ones. And so we work on designing subsystems that can address parts of these problems and then stacking them both laterally and hierarchically with very clean interfaces in order to break the problems down. And then we send sort of relentless innovation and optimizations of these subsystems with all of the other subsystems around it abstracted. And in addition, as we advance technology, we often build new systems where we construct them on top of or within the framework of earlier ones and keep upgrading. And that's been a very powerful tool, which has allowed us to reach where we are today. At the same time, this method of operation necessarily results in a lot of siloing, of really where we can focus on highly optimized subsystems, but that may not be the best use overall in terms of the use of energy for the whole system. So each part may be optimized for what it's doing, but without a view of the whole system, we often sort of have something that's locally optimum, but globally far from optimum. And moreover, a lot of challenges at the subsystem level are often addressed or papered over by essentially throwing energy at the problem. There's some more energy you throw at the problem, you can kind of address some of the real major challenges. And the problem is that this usage of energy often compounds among the systems. So the overall system draws far more energy and has far more environmental impact than really required. So it seems that taking a systems perspective and rethinking the subsystems and their interfaces is really an essential step to dramatically improving sort of these computing and communication systems as a whole and mitigating their climate impacts. It is a very challenging thing to do, as I've seen from personal experience, bringing in kind of new paradigms and sort of breaking out of this subsystem mold in order to achieve a global benefit. But when you can do it, it really can have a large impact. And I think this is also an area where we can marry the strengths of industry and academia to really achieve these dramatic improvements that we're seeking. So I am really excited today in this session to hear the thoughts of our speaker and the thoughts and questions of our audience. And so I'd like to introduce him. Sam Nafziger is an AMD Senior Vice President, Corporate Fellow, and Product Technology Architect. He works across the company to optimize product technology choices and their deployment with a continued focus on driving best practices to maximize product competitiveness, efficiency, and cost. So he's really looking at the level that can really bring a lot of these benefits. So I'm really excited to hear what you have to say about reducing the climate impacts of computing across all scales. So Sam, please go ahead.
Great, thank you, David. Well, I'm super excited to be here, and it's a topic near and dear to my heart, my focus. And I love talking about our technology and how it improves efficiency and environmental impacts. So I'll jump in here talking about the broad view of architecting for efficiency. Like David said, it's a system level problem. So the landscape, to start with, is that a big contributor to compute power consumption is the accelerated computing, and that involves a number of different components, different markets, high performance computing, AI training, as well as many more satellite market areas that share the intellectual property components and the silicon devices to support those markets. So these are growing very rapidly, and I'll show you some data along that line. And that results in a lot of energy consumption, especially combined with the fact that the energy use of these is increasing due to a number of technology factors. So we, at AMD are focusing on win-win solutions that improve the efficiency of these products while also benefiting the environment and delivering the compute performance that the market demands. And the market demands have been escalating even more rapidly than in years past. And one of the great examples that's easy to track is the performance of the world's fastest supercomputers. And as you all are well aware, these installations are used to solve many pressing real-world problems that affect humanity, the future of the planet. We deploy into these giant installations that do protein folding simulations, model the climate, support exploration for new energy sources, and many other different pressing and high-value problem sets. These systems they've been doubling their performance every 1.2 years or so. If you just run that trend line through, that's using a metric of a well-known metric in the industry, LinPack gigaflops, double precision floating point, and this growth rate significantly outstrips Moore's law, which is approximately 2 years doubling. And so there's a lot going on in these installations to drive performance beyond just the silicon CPU or GPU level, but delivering performance at the system level, which underscores the value of optimizing that entire system. Another great example is different but shares common components, the gaming market. And gaming is highly compute intensive to render these images in buttery smooth, high frame per second quality while providing high resolution features like ray traced imaging and lighting that greatly improves the realism of the experience. Our world is paying a lot for these gaming systems, and their usage has been growing dramatically worldwide, with esports rivaling many physical sports for investment, advertising dollars, and interest levels and viewership. So the underlying performance that supports these improvements in the gaming experience can be boiled down roughly to floating point operations per second. These are lower precision floating point operations typically than for supercomputers, but it's been growing at a similar exponential rate. And there is no indication that these growth rates are going to abate, which means in the next few years, we're going to have to find ways to deliver a tripling of the floating point performance of today's GPUs to meet the market demand. Obviously, we do not want to be tripling the power consumption of these processors, so innovation is going to be required. Another great market to talk about as an energy consumer is machine learning. And there are basically two classes of machine learning application. One is on the inference side, where the smartphone or laptop uses a pre-trained network to accomplish its function of maybe language translation or image recognition or background blur. other effects. Training those networks is what takes most of the energy. It takes a huge amount of energy, and these networks contain parameters, which are the things that get trained to do their impressive recognition functions. And to reach human levels of capability in these different applications requires a lot of parameters. And we're all beneficiaries of the higher accuracy of these recommendation systems or natural language processing systems. But the parameters are growing at an astonishing rate. Forget 2 years or 1.2 years, we're talking 2.3 months for a doubling of these parameters. And that means we have to invest the compute time to get the correct value on each one of those parameters for the system to deliver its accurate function. So these capabilities are consuming a very large amount of energy. And in the face of all that growth and demand, we are, of course, dealing with the Moore's Law slowdown that has been much discussed. And so we all know that the technology nodes aren't what they used to be. The introduction rates are fewer and far between, and they are delivering less, even though they come later. Combined with that is the increasing cost of these process nodes and the increasing die size of our processing elements. Those you might not think are directly related to energy, but as the costs go up for the most advanced node, that means we are motivated economically to use less advanced nodes as much as possible. They are, of course, less energy efficient than the most advanced node. And the large die size problem means we have to start splitting up our designs into multiple smaller chips, which of course requires communication between them, less efficient than a single piece of silicon. So these are all some of the factors contributing to the fact that the, just taking an example here, the absolute power of the top supercomputers is going up significantly. And that's to deliver that, doubling every 1.2 years. And this is just a sampling, many other examples of how power consumption is increasing in the compute space. So we have a lot of challenges with the energy dimension of our compute demands worldwide. And this has been codified nicely by the Semiconductor Research Council with a report that they put out in the Decadal Plan a year or two ago. And it showed the growth in compute demand as shown in this green curve as boiled down to the energy consumption in joules per year. And it's on an exponential growth path, which given what I just showed earlier, not surprising. And we can see that in 2030 or so, we're getting to very sizable fractions of worldwide energy consumption, and that's problematic. We don't want to be increasing energy consumption worldwide for a host of environmental reasons, and if compute is consuming a very large fraction of it, then we have a significant worldwide issue. So we need new approaches to meeting this compute demand, because when we look back at the efficiency of general purpose processors as plotted here from 1971 up until 2020, a very interesting observation can be made that as we have increased the performance of these processors, that's the y-axis, the instructions per second. So everybody wants higher performance processors. They do their computations faster, the quicker response times, we can do more complex tasks. But the x-axis here is the bits switched to deliver that processing performance. And this is a log-log scale. You can just see by the slope of the curve, it takes a lot more bits to switch to deliver a small increment of performance than the actual performance improvement. So we're really at about a 2/3 log improvement rate here, which is, if we're going to be growing the compute demand as exponentially as I just showed, we need a much more aggressive trend on the improvement in compute efficiency. And so that means we're going to need new approaches. And a clear opportunity here is with more special purpose domain specific accelerators. And shown conceptually, the value proposition of these accelerators is that they do a smaller number of things much better. A general purpose CPU, if you just look here, applications and the performance per watt, the general purpose CPU is great because it's ubiquitous, easy to program, and the application set it can use is very broad. GPUs have gotten quite a bit of traction in a number of markets outside of just gaming because they do the highly parallel throughput computing and can deliver much better performance per watt on those sets of workloads. Now you try to get GPUs to do database processing, for instance, they're going to be very inefficient because their whole microarchitecture doesn't apply there well. And then in the the red here are more special purpose accelerators, and a great example there is some of the machine learning training and inference architectures that are proliferating. They are great at those specific tasks, but only at those tasks. So our application-specific accelerators is going to be absolutely essential to improve the performance per watt, meeting that compute demand. And in addition, in the face of those technology challenges I went through on the process technology, the silicon technology, we've got to get very good at doing chiplets, which is now becoming an industry term for disaggregating what would have been a very big single silicon chip and do multiple components and specializing those components for higher yield and efficiency, and then putting them together with low overhead interconnect. And this is moving to 3D, which I'll talk a bit more about later, which has great promise for not only improving raw performance, but the efficiency of each of those compute instructions. So modular design and application specific are going to be very critical elements to improving our performance per watt. And another area is on the algorithmic side. There's been a lot of research that's accelerated recently in the face of the machine learning, the importance of machine learning around making better use of the bits in our floating point operations. That's the way I would put it. So we've been using, for it seems like forever, my entire career, the IEEE floating point 64-bit and 32-bit formats. We have an exponent and then a mantissa for the fractional component. And these are the mainstay of high performance computing tasks. It's how we measure performance level in those supercomputers. And these formats, they're great, they are robust, but they are overkill for a lot of applications. So we're finding in the gaming space that we can make use of lower precision math and deliver an image that looks just as good with 16-bit computations as when we use 32-bit computations. And a lot of great research there. And of course, in machine learning, we are pushing down to much lower precisions, or we're moving bits around from the mantissa, like in this BrainFloat 16, it's 16 bits worth, but instead of a big mantissa, we drop a few bits there, put them on the exponent, we get greater range for those computations, which helps those algorithms converge faster. So we get higher performance with the same number of bits, which means it takes less energy to train those billions or trillions of parameters that I talked about earlier. So research in these math formats is a great area for collaboration, finding the right format for the right task. It's kind of another dimension to the accelerated computing thing I just mentioned. Algorithmically, we can accelerate certain workloads with lower or special precision math and get more done with less energy and less time. And plotted up here, just which I didn't talk to you, is the energy consumption. And the thing to note is, first of all, CPUs, they're very general purpose, critical to the industry, but they are not the most energy efficient when it comes to just pure math computation. You run those same 32-bit computations on a GPU, the energy drops by about a factor of 3. And then if you cut the precision in half, it drops even further, and 8-bit down again. So when we can craft our algorithms through software and the equations used, et cetera, to converge with lower precision math, we're much more efficient. So now I'll talk through some of the recent AMD product results, which provide higher efficiency, and make some comments as we go. So this is what we call our Instinct line, which goes into that high performance computing space and the machine learning space. And so these are the big iron computing elements, you might say. And we've been making significant generational improvements here on the left in the absolute performance. So peak teraflops per compute device, and we track these in mainly we would 2 different categories, although we have multiple precision supported. The FP64 here is the most important one for those supercomputer deployments. FP16 and its derivatives, most important for machine learning training, and you can see the gains in absolute performance here, pretty substantial generationally, especially when we're talking just 1 to 2 years between generations. So this is the sort of improvement that supports that compute demand I talked about earlier. Now you'll notice, your eyes may have been attracted to the power number down here at the bottom. You can see that the thermal design power for these GPU compute processors has been growing. And a number of reasons for that. One is we're doing a lot more computations in these devices, but the other is, as I mentioned, the technology nodes have been slowing down in their introduction and improvement rates. And in fact, these last 3 processors are all fabricated in TSMC's 7-nanometer silicon. So any performance per watt gains we get don't come from silicon improvements, they come from architectural and algorithmic gains, or through chiplet design approaches. And you do see substantial performance per watt gains here on the right. So FP64 in particular makes huge improvements. We go from 0.038 to 0.171, so about a 4x improvement in the flops per watt with this MI250X processor, which is great. It means that exaflop supercomputer that we're deploying all of these into is going to be much more power efficient than the ones that had gone before, despite the fact that it's in absolute terms higher power, but it does far more watts than the power increase. Sorry, it does far more flops than the power increase. Now, you can look here on the right and say, well, what's wrong with the FP16 performance per watt? It didn't, it took a big leap here from MI60 to MI100, but not so much to MI250. And this points to the power of the architectural improvements that these designs can exploit. And what we had done in moving from MI60 to MI100 is implement dedicated matrix math pipelines in the design, which are optimized to do the general purpose matrix multiply functions that are most common in machine learning training algorithms. And when we organize our data path to do a whole bunch of floating point operations chained together in a matrix multiply fashion, we have a lot less data movement and a much more efficient floating point operation. Since we already made that move for MI100, and the technology didn't improve, it was more difficult to increase the performance per watt without that big architectural enhancement. So this shows both the power of architectural improvements and the need for continued innovation in that area. So I want to switch and cover a bit about EPYC server, CPU server processors, because CPU servers are still the largest energy consumers in the data center worldwide, and it's critical that we have a great performance per watt story and long-term plan in this space. So the we're very, I have to say, you know, at AMD, very proud of our EPYC servers, which have substantially higher performance per watt and have had that for many years relative to the competition. And you can see here how that boils down, and that in order to perform the same amount of work, in other words, a 10,000 integer score, so we have a certain amount of computation to accomplish, and you can do that computation on either one of these systems. On our competitor system, takes 17 servers to do that. We can get the same work done with just 12 servers, and that means we consume not only less power in the process of accomplishing that compute task, but we consume fewer resources to actually build and manufacture, and the energy that goes into producing the sheet metal and the silicon and everything else for these servers. So the higher performance of the servers and the lower power consumption combine to have significant environmental benefits. And it's an area that obviously we're going to continue to drive. And another aspect in the CPU server space that needs to be understood is the virtual machines. And the way the cloud works, of course, is basically the data center owners rent out the compute capability of these machines to whoever wants to rent them. And they are divided up into virtual machines, which run the tasks of the customers. And the fewer physical machines required to run these virtual machines, the more efficient the computer is going to be. So you can see here, you know, once again, we're pleased with the results that we've been able to deliver, and that we can serve the same number of customers with a given amount of compute measured in virtual machines with significantly fewer sockets. And that means that it's lower operating cost, lower hardware acquisition cost, and lower energy footprint in the process. So higher performance and lower power per operation are big levers in the environmental improvement space. So I'll wrap up the product level view here with high-end gaming, because this is an important energy consumer worldwide, and another area that we've been focusing heavily. Like I said, it leverages a lot of components common to the compute space, that Instinct line. And I'm especially pleased with the results we've done, because once again here, these are the same 7-nanometer technology, but we've managed to, through architectural enhancements, drive up the performance per watt by 50% at least each generation, which is a difficult task to achieve, because it requires innovation at the architectural, at the silicon level, and at the software and algorithmic level to accomplish. One of the ways we accomplish that, just give you an example of the kinds of innovations we need to do, is in leveraging very high density on-die fast SRAM memory to decouple ourselves from the DDR memory that serves the GPU and traditional implementations. That GDDR6 memory, it's very high bandwidth, special purpose for gaming, but it consumes a lot of energy per bit transferred. That's the 7 to 8 picojoules per bit, and that's a good measure of the energy efficiency. If instead we are accessing those bits from our on-die, what we termed infinity cache, it only takes 1.3 picojoules to get that same information. So clearly, if we can implement this cache and most of the time go to this infinity cache for our images and image and rendering information, we can generate much more bandwidth per watt, higher performance per watt, which is exactly what we've done. So these kind of architectural enhancements are great areas to collaborate with academia on, finding more energy efficient ways to deliver the same or better performance that we need to supply the world's demand. I'd be remiss if I didn't talk a little about 3D, which I think is one of the most exciting vectors of innovation in our field here. And instead of designing just planar silicon, we are exploring ways to stack multiple pieces of silicon on top of each other and get significant benefit from that. And we have just productized what we've called a Vcache design that stacks a very highly dense SRAM cache to supplement the existing cache on the baseline compute chiplet die, which is here. And that increases performance substantially by about 15%, which if you're in this industry, you know that 15% performance is basically a generational performance gain, very hard to come by. And we have managed to do that with just stacking this additional die on top and connecting it up properly. Now, the better thing about this is it delivers that performance in a power neutral way. So we didn't have to add higher power CPUs. We didn't have to raise the frequency and voltage. We just put this cache on there, and kind of like with the Infinity Cache on the prior slide, we save energy by accessing this local high density SRAM instead of going out to main memory. And the other great thing about 3D that we talk about here is the fact that it's intrinsically energy efficient, because it reduces the distance that bits have to move to get to where the consumer is. So with 3D, and you can see the spaces here, you know, so we've been doing chiplet designs for quite some time. We have multiple die on the package substrate. To communicate between each other, they have to go down to the package substrate on these long routes. These are thick copper wires. So if we'd put the additional SRAM down on the substrate, like where this IO die is, we would have to be transmitting those bits across this, this energy consuming interface. But instead, by stacking it on top, we have these tiny little through silicon vias that connect directly to where the data needs to go. So dramatically less energy, you know, 3x reduction in energy per bit, and that's actually greater. That's relative to alternative 3D stacking. Against 2D, it's 10x or more. And the interconnect density is dramatic. And so the benefits of this are many. We can enhance the compute functionality without growing the power consumption. We can stack heterogeneous compute die, special purpose accelerators, to get their energy savings and have the data very local. So we are excited about the promise of 3D. Look forward to more ways of exploiting it. So I'll just spend a couple minutes on how we are turning all of those innovations and the challenges that we see into a goal to improve our efficiency by pretty dramatic amounts in the coming years. The context for this is just a synthesis of what I went through before. If we look at the volumes that are expected to ship in future years, based upon industry watchers, and with our knowledge of how much energy each of those compute nodes is likely to consume, we can plot out the energy use over time. And the biggest energy consumer today is, like I mentioned, the CPU data centers. Those are the general purpose compute devices, millions and millions of them out there. We need them to run all the daily tasks, financial calculations, everything we depend on. But we have the high performance computing and machine learning data center deployments growing much faster than the CPU deployments. And the energy consumption of these is growing quickly as well, partly because of the exploding demand, like I mentioned earlier. And we see these things converging out in the 2030 or so time frame, which really wasn't even comprehended in that SRC decadal plan outlook. So this is a big area of concern, and it's something that we believe innovation can help address. And so what we've decided to focus on is improving the energy efficiency of these compute nodes that service those markets by a factor of 30 over the next over the period of 2020 to 2025. So we announced this goal last year, and we focused, you know, talking about system level thinking. We decided instead of just focusing on a CPU or a GPU compute device, we want to focus at the next level up in the system, which is what we call a compute node. And the most commonly deployed compute node today is what we call a 4P. We have 4 of these GPU accelerators, which can be used for machine learning or for high performance computing. And they are controlled and managed by a CPU server device here. So if we look at this, these are typically built on a single motherboard and co-located. And so we're focusing on the energy efficiency of this entire compute node. And we want to drive that efficiency as measured in performance per watt up by a factor of 30 by 2025. Relative to the industry rate, that's more than double the improvement. So the industry's definitely been improving. I showed you some examples from AMD's product lines, but that improvement rate is insufficient to meet the compute demands of the future without exploding energy and causing a significant environmental detriment. So we want to accelerate that improvement rate. If we tally up the amount of energy that saves, it's a lot of kilowatt hours, and that translates into a lot of metric tons of carbon dioxide and other metrics you can read there. This is a number not that we expect AMD processors to consume, but it's a theoretical that if all of the data center deployments were to adopt our 30x improvement goal, this is how much could be saved. And clearly, we want to have a big share of that market. But the point is, it's a big opportunity. These data centers are large energy consumers. So we intend to hit that 30x goal, and assuming we do, that frightening trend in machine learning and HPC energy use is going to drop substantially, and as per the green line here. So this is the industry line, and if we hit the 30x goal, we end up in a much better spot. And obviously, we will be focusing aggressively on CPU data centers as well. So we're excited about this. These kind of big, bold goals, we don't know exactly how we're going to achieve them. I went through some of the tools in our kit that we think we can use: 3D stacking, lower precision math, algorithmic improvements, all these approaches, efficient caches. Some mix of those will be necessary to get there. It's a good way to rally the teams and the engineering teams in the company to focus on power efficiency and come together to deliver something that's really breakthrough. So we're excited about achieving this goal and the innovations that will be required to get there. And it's not just the compute devices themselves. As a company, we are absolutely focused on improving the footprint of our company operations, working with our suppliers to improve their operational efficiency, reducing the waste they generate in manufacturing our products. And we're looking to get to 100% of our supplier factories having a responsible business alliance audit and reducing their greenhouse gas emissions as well. So excited about the bold plans we have as a company and the technology required to get there. We love innovating. We need partners in innovation and finding solutions to these challenging problems. And pleased to be able to talk to you today. So that concludes my presentation.
First, thank you for a really enlightening presentation. I think you've really shown some of the dramatic challenges that are happening in compute, both in high performance and machine learning and in general, and where that's taking us from an energy perspective. And it's, I have to say, rather sobering. And you've done a nice job of pointing some of the directions that AMD is taking, and also some of the directions that academia might take towards helping things like the formats of data, architectural enhancements, 3D packaging. I'd be curious to understand from your perspective, what do you think in terms of achieving this very aggressive 30x goal you've set for yourself? What do you see as the highest tentpole? Well, like if somebody could hand you a magic technology, or at least the start of a magic technology, where do you think that the biggest single opportunity, especially coming from sort of new ideas, would be? That's a very tough question, I know.
Yeah, it's a tough question, and I'm more of a hardware architect, so I gravitate towards those examples and can talk to them in great depth. But actually, I would say it is in the algorithmic and software side, and adapting our software solutions to make more efficient use of the hardware. And that can be subdividing problems differently, and like I touched on, making use of lower precision math operators to accomplish the same result, which requires innovation, proper use of the system level architecture. So data movement is our enemy for energy efficiency, right? And simple programming approaches that split up the problem and then have to combine results in a central location to do the final computation. Those are inefficient. So figuring out to be more localized, minimize the processor to processor communications, minimize the amount of memory use, keep things local on the silicon instead of moving it off to DRAM. All of those approaches, I would say, are probably the single biggest lever and the greatest opportunity for research and collaboration. Now, we have a lot of exciting things on the hardware architecture side, which I would say is they're the sum of a number of smaller improvements that together add up to large gains. But I can't point to any one of them and say it's great. I mean, the 3D thing is obviously going to have an impact, and the matrix, the dedicated matrix math pipelines are great. We're going to see more and more of those, and don't want to keep too protracted an answer, but that's an example also of a software hardware synergy sort of approach, where we recognize the common loops and operators in software and implemented those hard coded in our compute devices. And so I look forward to more of those opportunities as well.
That's very interesting. Let me ask you a slightly broader question, as somebody who has a view sort of from the top and at the system level. I alluded to earlier that, when you have some big innovation that sort of breaks out of an existing mold of how things are being done, it can be very hard to introduce it into product lines where it doesn't fit with sort of the existing paradigm. And so I'd be curious to, understand, what is AMD's approach towards enabling those kind of things to be brought into play?
Innovation is difficult. I agree. I mean, we can look at things like optical interconnects, which have been on the horizon for many years, and they continue to largely be on the horizon, but they are intrinsically more efficient. And it's economic drivers that really get any industry and company over the hump and adopting new approaches. So the demand has to be there for these new, more efficient approaches, and then that drives the research and development to enable it. But what I would say, so that's kind of the glass half empty view, right? What we are doing, what I'm committed to doing, is trailblazing innovations that are ahead of their time, and so that they are ready to be adopted when all of a sudden the economic drivers are there for it. And so that's my goal, is to have incubation internally of some of these capabilities, and then when the time is right, we can be much more quick in deploying them. And that requires, and that's what academia is great at, having that longer term view of where things are going, and 5 years from now, what are some of the improvements that are needed, and then we can start on those earlier and be ready for them.
That's great. I'd like to turn perhaps to some questions that are coming in, and one that came up, and it's sort of very topical to the modern time. Since crypto mining and proof of work kind of energy consumption is growing heavily, sort of what are your thoughts in sort of addressing those challenges? And you could, and the question also asks about, the efficiency of current ASICs, but also things like the cooling challenge, addressing the cooling challenges for these kind of parts.
Yeah. Yeah, I have to say on the cryptocurrency mining, yeah, proof of work and those things, that is a big energy consumer. I know there are new currencies being defined and deployed that require less energy to mint new coins, but fundamentally it's just highly compute intensive, and there's not a whole lot in our toolkit to deal with that. Other than having the best power efficient silicon that we can design, which certainly we're doing. And yeah, that creates a lot of heat. And I would say, immersion cooling, it's a reactive approach. It's kind of a necessary way to deal with the heat being dissipated without melting down the silicon. So it's not really a way to get to energy efficiency or to deal with this particular challenge. Special purpose devices, like I said, the domain specific accelerators are done right. They are intrinsically much more efficient than general purpose, right? So coins that get a lot broad adoption warrant special purpose accelerators to mint the new ones, and that certainly is the best way. But that's a risk if you're going to invest a large design team and pay for the silicon to do these things.
Sure. Another question that came in, and I'm going to ask both the question they had and something I was curious about myself. The question relates to, you're referring to the data formats being and sort of changing how the math is done, being a nice driver in terms of getting very high performance in things like ML training. And so the question first is, are those kind of data formats dial up, dial down, or do you have to architect your whole chip around it in terms of a particular data format? And the second question, or the related question to that, would be, if you're doing special purpose hardware for training and sort of data formats for training, which is as you mentioned, the very energy intensive part of ML, do those data formats traverse right over to general purpose hardware for the executing the train network?
Yeah. Okay. So a lot of good questions in there, and this is, I think, one of the a very exciting area for improvements and for a lot of innovation. So does a consumer get locked in? And that is a big problem, right? I mean, we have to choose when we design our hardware, how the transistors are going to be hooked up, and we hook them up to do certain formats of precision math. That's the way it is, and then the software has to adapt, and maybe the research and algorithmic innovations lead towards a different format than we chose to implement, and that's highly problematic. So there is work going into more adaptable data paths and flexible positioning of the decimal point, for instance, between exponent and mantissa. So there's a certain amount of adaptability we actually can put in areas like this, but we need, I think that's an opportunity for improvement. So because there's a tension there, right? We want to use the new formats, but silicon takes a really long time to design, and software evolves much more quickly. So there's a challenge there, and so we're putting as much flexibility as we can. So you mentioned the training and then the inference side, using the trained elements to accomplish the tasks of speech recognition or whatever. Those tend to have very different precision demands, and for training we have to converge the algorithm towards a good set of weights on all those billions of parameters. And that convergence time is what sets the energy cost and the expense of training the network. And so too low a precision and the algorithm doesn't converge. So that's the challenge that we have on the training side. But then on the inference side, we receive those parameters, and typically much lower precision can be used. And in fact, we go down to integer 8 or int 4 instead of 16-bit floating point for training. The precision used for inference can be influenced by how the network is trained as well. And so we can train a network for a specific precision of inference. So if we're seeing the most energy being consumed actually in inference, because let's say we're deploying a trained network out to 10 million different edge instances, or smartphones. Well, that the energy used with high precision inferencing could swamp out the energy used to train the network in that case. So we can invest more energy in training a network that supports lower precision inference, and we end up ahead from an energy footprint. So a lot of interesting exploration needs to be done there, how to optimize this.
That's kind of very excellent detailed answer to the question. You mentioned a few places where sort of industry and academia can kind of collaborate and sort of making sure to be ready to absorb sort of new ideas when they sort of become viable by the driver, viable in terms of the market sense. I'd be curious to understand in these evolutions of these products, you've just sort of shown how they've gone along. As with a lot of the fab, the chip outputs and the fab costs, are the deployment costs of a new generation of systems for you rising dramatically with these sort of innovations, or can you kind of keep that curve flat, if you understand what I'm saying? Because if it just grows exponentially, you can't do it, period, right?
Yeah. The economics of developing these is very challenging, right? Because these new technology nodes are not only is the cost per transistor flat or rising versus the Moore's law of the past, but the mask costs and the wafer prices to generate these devices is going up pretty dramatically too. So the barrier to entry for designing processors is rising, right? And it requires bigger companies to do it. The reason bigger companies can make that investment is because we amortize that sunk cost of developing it, manufacturing it across millions of sold components. So we need a sizable market to justify the development cost for these things. And that is at odds with what I just was saying, in that domain-specific accelerators are one of the best ways to improve energy. Well, as per that little bell chart I showed, domain-specific, they accelerate a small set of workloads, which means their market is smaller, right? So now instead of 10 million, you only can sell 1 million of these special purpose things. Sure, they're really efficient, but now their costs are going to be really high, right? Because you got to amortize over fewer. So we have a real tension there, and that's why I'm excited about the modular architecture that I briefly mentioned. I could go into great depth on how we're doing that, but when we can design small components, maybe 3 different accelerator types, and mix and match differing numbers of those to provide accelerations appropriate to a given set of workloads, the amortization of that sunk cost that I just mentioned can once again be over a much broader, much higher volume set of parts, because we're providing differentiated individual products by mixing and matching.
Oh, that's actually, and that is one of the challenges. That's really interesting. I'd be, sort of related to that note, I'd be curious to understand. You mentioned needing the space, needing the market, and the ability to make the chips. What do you see as the key partnerships across industries that are most important for better adoption of more efficient computing?
Yeah, well, yeah. So there are so many deployments of these compute devices, and into automotive, for instance, is a really big market, and the smart homes, and cellular base stations. There's just a huge breadth of deployment areas, and they have different power delivery, heat dissipation constraints, And so specializing our designs for these different markets requires collaboration with each of those segments to understand their needs. And to the extent we can design adaptable products that are right-sized in power and compute and cost for those markets, we'll be much more successful as an entire industry and ecosystem. And that does get back, once again, the modular architecture is a very powerful way to get there. And but yeah, there's a broad set of collaborations necessary, and that's another great function I think of academia is bringing different groups and voices and diverse industries together, because a lot of times it just takes talking together to see an opportunity in a way, like stuff we already have, in our toolkit can be applied in new ways to help the problem. So.
No, that's very good. And maybe as a final question, as you said, there's barriers to getting these things out there. Do you have suggestions for incentives or ways to connect either with your sort of customers and partners in the whether it's the automotive industry or the gaming industry or cloud, or with academia, that sort of would help lower the barriers to sort of getting innovations into the systems and then out to the customers?
Yeah, that's great. I mean, I know foundries do multi-project wafers that help lower the cost of entry. So they have one chip, and then dozens of people contribute little pieces, and then the manufacturing costs are divided. So that's already in place. One of the things we found, I mean, we just completed an acquisition of Xilinx, the programmable logic company, which was a very big investment. But one of the reasons we did that is it enables adaptation. So field programmable gate arrays, right? They enable configurability for particular markets, algorithms, compute needs, and that enables us to more specifically address these different market segments. But the other opportunity it opens up is prototyping of new approaches and algorithms in an FPGA and programmable logic that is much lower barrier to entry than designing a custom piece of silicon. Sure, it runs slower, but often, I mean, it's within an order of magnitude of custom silicon, and so it enables a genuine look at whether this is a good idea or not. And so I do think that's a very promising area, using programmable logic arrays.
Very interesting. Well, I think this session has given a lot of food for thought, both where the trends in compute energy are going, and what are how the challenges are evolving, and some of the directions that can be taken to attack those. And so, first of all, I'd like to thank you for a really stimulating presentation, and to the audience for some interesting questions. I think there's clearly a lot to be done and a lot of challenges, and I'm glad to see how seriously AMD is taking them. So thank you. I will just let everybody know that we will be taking a short break, and then we will be resuming in approximately 15 minutes for the next section of our workshop. So thank you very much.